So we'll call this one Custom Oscillator, just to be a little different. I hope this works. That was not an expected problem, so hopefully this will solve it. I suppose I could just drag in. Well, since I already did this, it'll be a little bit faster and show you a different thing. So we're going to go to my AudioKit directory and pull in AudioKit as a dependency that way. So that'll be another way of including AudioKit, slightly different. When you do it this way, when you drag in the folder, you do have to add it as a dependency, as a framework manually. But let's make sure that builds. I'm trying to make the screen. I hope the font's okay, guys. I'm not going to show the editor only. Okay. So let's get started with importing AudioKit and hitting build. Okay, so it looks like it is building AudioKit up there. All right, so how to get started. So I'll just make a very basic app from the UI perspective here, and then we'll make it customized. So I'll make the conductor. It's going to be set up basically like the cookbook is set up. Create the audio engine. I may have to, it's not letting me, it's not auto completing only because it's still building. And we're gonna, for now we're just going to use Oscillator from AudioKit. And on init, we can set the output. Well, let's make the oscillator just a little bit more quiet and set the output to be the oscillator. And then start the engine. Okay. And so in the view here, see if this is now building. Build succeeded. So it does that sometimes where it says an error here, but because build succeeded, I think everything's going to be okay. So we'll create our conductor, and then we will just make a simple UI element to start and stop that oscillator. Something like if conductor.oscillator is playing conductor.oscillator stop. I could have done this in a ternary, I suppose. Okay. I think, let's see if that runs. Make sure you guys can hear it okay. Okay. So I don't hear anything. I assume you guys don't hear anything. So something is wrong. Let's see. We can print whether the conductors, whether it thinks it's playing, so we can find out where the problem is. Okay. So it does think it's playing, and we show no errors down here. So I hope that this is just a problem with the Zoom connection.
Do you not need to set the amplitude after you start the engine?
No, that shouldn't make any difference. Even if I comment that out, it would just be louder. For amplitude, there's only a few things that you have to start after the engine, one of them being mixer volume. but this should persist. All right, so I don't see what I did wrong here. I don't think there's anything wrong in the code. I feel like there could be something wrong with our audio setup. So one way of testing that, I suppose, would be to put another UI element here. Stack. Don't need this padding at all. Put in there what an FFT view. We have to import AudioKit UI to do that. I can do that like this. And again, since we're doing this manually instead of with Swift Package Manager, you'll want to do that too. So let's see if that is building because I don't see auto completion yet.
So just to confirm what you're thinking, Ari, I copied what you did and it does play.
Okay, that's really weird. So let's see if this view, we're getting our sound. There could be something. Okay. This is okay. There's clearly sound for Matt, and there is something coming through, but I think this is just a problem with Zoom. I wonder if I feel like I did say share computer sound, but Marcus, you think I should stop the share and restart it? Okay, let's just try that. You are, yeah, it says you are, but let's try share screen, stop to share sound. Okay, and I'll quit this and I'll replay it. It might be super loud. So if you're wearing headphones, because I did take that oscillator 0.4 out. So I'll just run it for like a split second here. Okay, I heard that. Did you guys hear that?
Yeah, put the yeah, there you go. Put that back in. Cool. So it's just a Zoom setting. Ooh.
Okay. Yeah, that's the way it goes. Reasonable volume for everybody? Yeah, okay.
How about a little lower? Tiny
a little lower? Okay, let's go to
like
0.1 then. Okay. Well, I will just not do what you tell me to do. I will always do something like that.
I love that about you, Ari. I love it.
All right, so we have our default oscillator. So now we want to create our own custom thing. So let's do that by first creating a Swift file for the node. We'll call it custom generator. In the end, it's going to do more than just being an oscillator. Okay. Now, what I like to do is go into AudioKit and find the thing that is closest to what you want to have be your own, and then kind of steal the code from there. So at least as a starting point, it's a good thing to do. So we're going to go into AudioKit, sources, nodes, generators, oscillators. I'm just going to grab the most basic oscillator here, copy the code out here, and paste it into our custom generator. And wherever we see oscillator, we're going to change it to custom oscillator. And one other thing, but that's going to be the easy thing. The other thing we have to make sure to do is to call this something new. If you're planning on using the oscillator alongside the project, it's just a safe thing to do, because otherwise you'd have two components that have the same 4-letter description, and that's how Apple's stuff works. So let's change oscillator to custom generator. Okay, so it's kind of interesting to see what is different in like what we're really changing. So these are text strings that help us find, associate like frequency with the actual audio unit frequency. So those all need to change. That's just a comment, and then the reference to those change. And then the creation string has to change. And that's it. So, but we have a ton of other errors. So what's really going on here? Can I find audio unit container in script? Can I find table? Well, that's because we are no longer, this came from AudioKit, but now it's outside of AudioKit. So we need to import AudioKit in here. And a lot of those errors should go away. Okay, all of them went away. All right, so this is just a copy of the oscillator, but it's a copy that we now can do stuff with. Like if you want to have different parameters, you just copy these, and we might get a chance to do that. But it's very simple, right? You just have a new parameter, and you're going to follow the chain down and basically copy wherever you see frequency, copy it to some other parameter, which I think we'll get to. So this isn't going to work yet because there is no create DSP with this custom generator. So we have to create that. And again, we're going to go to AudioKit and steal the source from there. So the AudioKit contains the Swift layer of things. So all these nodes are Swift things, but C AudioKit contains the lower level DSP, the C level DSP. And so we go to the same directory inside of C AudioKit nodes, generators, oscillators, and there is a companion file that belongs to C AudioKit that also we'll need. So this is I'll make this a little bit bigger. Whoops. This is a .mm file, which means it's an Objective-C++ file. And so we're going to create for our stuff right next to this. We're going to create a Objective-C++ file. And I don't know which one it's better to do. I think this one's probably fine. We're going to call it custom generator DSP. Is that what? .mm. Okay, at this point, because we're adding our very first C file, we are given the opportunity to create a bridging header. Now, we could create it, but we don't have to for what we're doing. You'll want a bridging header if you're going to actually call Swift code, C code from Swift or from Objective-C. So we're going to just skip it for now because it's actually not necessary for what we're going to be doing. So let me just check to make sure I got that right. Oscillator DSP. Okay, yeah. So I'm just taking all of the code from oscillator DSP mm. Oh, I actually didn't type this right. This has to be .mm. It actually looks at the extension to know what kind of file it is. So this thing knows that it's Objective-C++ now that we added .mm. So just like before, we're going to need to rename all of the oscillators to our custom generator so that it's differentiated from the oscillator in AudioKit. It's important to notice these. These are the things that actually connect the parameters inside here to things that can be called from AudioKit nodes. So if you do make a custom something, you have to register it the same way with this AK register parameter. I could go into more detail on how that's what goes on in there. It's kind of magical, but we'll see how much time we have.
Yeah, Ari, if we do have time, let's come back to that, because you know, this is a lot of copy paste, you know, for a single parameter. So just understanding how all this works would be really valuable. We don't have to do it right now because you know, that's not the topic of, but it'd be cool to understand how the magic works.
Yeah, definitely. So I just want to make sure that everything did build, and we can actually run it now with this content view saying our oscillator is no longer an oscillator, but our custom generator. You guys want me to change the name of this to make it even more obvious? So we're actually not just using an oscillator, so we're going to have other things associated with it. I could have done this with the refactoring tools, but it's okay. All right, so big deal, right? I did a lot of copy and paste, but the nice thing is, you know, this code now is our code. It doesn't live inside of AudioKit. It lives inside of our project. So if we want to do special things like secret sauce type stuff, we can do that here. So for instance, I can do one quick change to this. We can make another oscillator here that is our tremolo, say. And let's see, we can look for OSC. And so in our creation, we'll also want to do the same thing for our tremolo. And we'll just use the same table. Right now it's a sine wave. But I could change that in the code, and we can see a square wave as well. But so we create it, we have to destroy it. And if we reset, we have to reset it. But so this process block is where all the real DSP happens. So inside here, we need to set our tremolo frequency to be something. And I'm just going to set it to be the frequency of the oscillator, maybe divided by 220, so that it happens less frequently. Like this will be every half second if we're setting a 440 into it. So that's setting the trem frequency, and then we have to use it. So we have to calculate it. So right here where we calculate the oscillator for the waveform, we're also going to calculate the tremolo. And we're going to have our own temporary variable for that. So we can call it trem temp. And we're going to store the value into there, trem temp. So this is just calculating the next value of the tremolo temp value. And then we have to multiply this thing by trem temp. All right, let's see, I made a mistake here. Cool. So we have now the ability to use low-level C functions from SoundPipe, or from, you know, we could just put multiplications and our own calculations inside of here. This is just basically a C++ file, or, you know, we can do all of our math inside here in this process block, and we can have custom DSP. So that's like digging down one level into the DSP. We have now made our own interface, and like so. We can create also, like we wanted to make the, instead of what the kind of hack I did right here to make the oscillator, the tremolo frequency just related to the oscillator frequency, we could make this custom generator have a value that we can change for that tremolo. Do you guys want to see me do that?
Oh, yes.
Yes.
For all
Okay.
kinds of reasons.
For all kinds of reasons. Okay.
Yeah, and let's keep track of how many steps and how many places this happens.
Okay. So we're just going to go here and say we're going to make a trem frequency. And the identifier will be trem frequency. You know, you don't have to change all these things for the demo, but I'm just going to give you a sense for all the things that will change. Trem frequency. You know, it's really not the AudioKit way to do it like this. It really should be tremolo frequency. We're more verbose than that. So I'm gonna go like that, tremolo frequency.
I forgive you.
And the rate there, we're not gonna go from up to 20,000. We're gonna go up to like maybe 20, you know. And tremolo frequency. Okay, so that is defining the Swift interface for those things. We have to put it in here. Custom generator.trem frequency def. And we can also put it in here as a part of the initialization. Start off with the value of 1. And okay, so now we have, that's the Swift interface. I think I did that right. And then in here, we'll have to add some generator parameter for the tremolo frequency. It's going to be a good test of my typing here. Really just kind of looking for where, keeping my eye out where frequency has been used and just knowing that nearby that I'm going to do all the tremolo frequency stuff. All right, so that's that. Now in here, we're not going to do any of this get and step detuner type stuff. So we can just do tremolo frequency. I could make that one step, I suppose. Okay. And then again, I got this new parameter, so it has to be registered. The order of these things does matter. So it should be consistent.
You misspelled the registration parameter.
Thank you.
Tremolo.
Do you hear?
Yeah, isn't it tremolo? No?
Tremolo?
Is it tremolo?
Tremolo. Am I spelling it wrong the whole time? Tremolo? Tremolo. Did I spell it wrong every single time?
Is it tremolo or tremolo? What is it? This is my problem, not your problem.
I typed it this way over and over again. So if it's wrong,
never mind.
Somebody can look that up and give me.
I just said it's. You're right, Ari. I was questioning it though. I had typed it in the same way. So
tremolo. It sounds like, yeah, it's one of those things when someone says it, like, yeah, it does sound like tremolo.
Okay, so it's all consistent. So we're good.
Okay. All right. So let's put a content view. Let's use that thing and put a slider on here. I'm gonna have to do a little bit more than that. Probably do at published there. Observable object. Start off at 1.0. And when it got set, we're going to set our generators.tremolo frequency to that value. Yeah.
Why do some places have conductor.generator and this place does not? It just has generator.
This is the conductor.
Oh, well, what about the content view stuff? Yeah, there.
Content view has all conductor because it's referring to this conductor. So this would be self. Yeah.
That is okay. Thank you.
Sure. Slider. Conductor dot tremolo frequency. So I feel like that's not right. So we're going to find out. Okay. Okay. Let's see if we've got this working now.
Golf clap.
So that's works, right? So that was all the things that needed to change to get a parameter that's changeable. Anything else you guys want me to try to do with this? Because I want to now, next thing will be to talk about going one more level deeper.
I wish you could show me how to change the waveform, but I bet that's a rabbit hole.
Well, so, I mean, so one way to do it is just inside here. If I start this and make my custom generator be a waveform, you know, dot square. I made it quieter because squares are louder than sines. Now this should be a much harsher on and off. That's interesting. It didn't exactly go off. It kind of stayed on. I wonder why that is.
What's I'm sorry, you probably showed this earlier. Is the tremolo in the DSP layer? Yeah.
Oh, I know what it is. What's happening here is, so I did a little cheating basically, right? I was using the same wave that was going for the waveform. The waveform goes from -1 to 1, right? Like this. And I was using that for the tremolo, but that was giving me basically with a square wave, it was going from -1 to without going there. And so it was basically staying the same volume, but there was this click happening every time it crossed the 0. So what Matt wants to do, and what is right, especially right now that I see what's happening here, is we would need to have a tremolo waveform here that is table dot square, and that would be a different thing. And I'm willing to go down that rabbit hole.
Or you could just do an expression at the DSP level where you adjust the range from -1 to 1 to 0 to 1, right?
I
You could do
suppose,
that
but
expression. I mean, that's kind of what's fun about DSP is you can do that, right?
yeah, well, this way we can send in whatever we want. We could send in positive square, and that's
Oh, there
exactly
you go.
what he wants, right?
There you go.
So let's do it. So we need to now create something for this table. So make a tremolo waveform and start looking for waveform. Tremolo waveform. Table equals table dot. We'll say dot sign as well, so we can make sure that that's working. And set wavetable. This might be actually this might be terrible, because this could be showing off one thing that we can't do. So how do you do set two wavetables? Because currently we allow you to set one wavetable in AudioKit. It's a very good point. So what we would do then, yeah, wow, this is kind of a bigger jump through, but heck, we can try it. So we can't just use now a standard AudioKit thing, because AudioKit just lets you set that one wavetable on things. But if we look for the morphing oscillator, it might give us some hints on where to look and how to really do this. So this guy has a waveform array, and he actually uses this indexed waveform. So one trick way to do it would be just say we're going to use a waveform array, and the first waveform is going to be the one that we use for the waveform, and the second one will be the one that we use for our tremolo. So we could give that a shot. Let's see here. So waveform.content index 1 waveform array and array. So we'll have to do something like this, but a little bit. What's that?
Oh, nothing. I was going to say that's calling set wavetable twice though.
With an index, right?
Okay.
So we're going to do a similar sort of thing. Yeah, I mean, I think you're right that it's maybe not as hard as I think it's going to be, right? So set wavetable there, and then set wave. I wonder what this has as default here. Index is 0 by default. So yeah, we're going to do this with tremolo waveform. And let our index be 1. And I guess I don't even know how this is necessarily being used, so but I'll just follow the convention here. All right. So now we're going to be also looking at the morphing oscillator as a guide, because now inside here, the way morphing oscillator works is going to be the guide here. So it actually creates an array of F tables instead of this one F table. And it creates a set of waveforms instead of a singular waveform. And here's our, we probably need this. This is overriding something, I guess it's different than in, yep. Okay. And so our initialization here is going to be different as well. Oops, didn't copy that out. All right. Init. So that's going to be doing our F table creation and our copying. And we don't have an F table anymore. So Osmorph was taking in an F table array. We're not going to be doing that. We're going to have to be getting our F table, our FT array at the 0th element for this. First element for this. And our destroys are probably going to be a loop.
I noticed that some of that stuff is indexing to 4. Is that because of how many tables there were?
Yeah, that's right. So I could,
Okay.
I can do a search for 4 after I get this working
Sounds
and
good.
bring it down. Yeah, but good point. So this is going to just look like that again. Okay. So where are our errors? Because let's see, find out what went wrong here. Okay, so it doesn't like that is actually spelled wrong. Whoa. Okay. I don't know if that's going to be enough, but I'm willing to give it a shot. We've initialized it. Now we're just computing it. So we should now have a sine wave going through a tremolo waveform that is a positive square. So we should really hear it. Oh, crash. Okay. So that is on our creation here. It's inside ftable.c, but we're going to create it here. Oh, well, okay. Here's where we go and change your 4s to 2s, I think. See if that's any better.
You're a wizard.
All right. Well, that makes me really happy. I did not expect that question. I wasn't at all prepared for it, and it wasn't that bad to do. So cool. Anybody else want to trip me up? Or shall we go down one more level?
What is this level you speak of?
Okay, so the level I speak of is right now we're using SoundPipe modules to change our audio unit. What if we wanted not to use those SoundPipe modules? We want to have our own really low level C stuff too, or even our own SoundPipe modules that are not part of SoundPipe that we can create. I know you want to do this, Marcus. I'm going to do it anyway. This is the next step down.
Do it, dog.
Okay, so we're going to go create a file here. And we're going to call it, it's going to be a C file. And we'll call it custom oscillator. And we'll create that H file as well. Okay, and again, I want to use stuff inside AudioKit as a model. So we're going to go to SoundPipe and grab the osc.c file as a starting point. We're going to need that custom os thing, so I'll get rid of this header because that's not going to be relevant anymore. And we're going to change everywhere we see osc to custom osc. There's going to be a bunch. We didn't have to rename them all, but you know, just to be pedantic here, this is really our own file now. And so the next thing you need to do is the .h file here. We need to put something inside of here. So again, SoundPipe has its own H file, which actually has every single thing inside of it. So we're just going to find the osc one. Actually, maybe I'll search for SP osc. Okay, so we're going to copy this down to here into our H file. And again, replace osc with custom osc. Let's see if I got them all here. Place. Okay. All right, so now there's some problems here, right? Because we didn't, these are SoundPipe-y things, so we're going to need to include, since we're outside SoundPipe now, we're going to have to include SoundPipe.h. Well, that's not completing for me. All right. Now that worked. That's building, which is kind of surprising because I actually expected it to fail. But let's try to use it. Maybe it's just not linking because it's not being used anywhere. So we're going to go to our DSP and we're going to say that our oscillator here is actually a custom oscillator. And we could do it for tremolo or the waveform or both. I don't know if it really matters. Anybody have any preference? I think I'm just going to do it for all of them, just so that they're all changed. So I'm going to change. See, I'll look for osc and see if I have what I need to change, and I'll paste in custom as needed. So this is going to be our custom oscillator. paste. Ugh. Paste. Okay, well, I type it. Okay, so these are all going to be our custom oscillators. Again, custom oscillator.
How do you type on multiple lines?
I'm holding down Option while I'm dragging the cursor.
Okay, awesome.
Yeah, it's a cool little trick. I think you can also do down arrow with Option. Okay, so I think that's good. Okay, so this is good. Now there's some problems, right? No, it doesn't know about this. Well, that's because we were just including sound pipe. We actually now want to include custom os.h. Okay, so build failed, unknown type name. And it's for these weird reasons. So I'm going to show you guys two different ways to solve this problem. And I just learned, like, I consulted with Taylor like yesterday on how to do this. So if he were here and I did invite him to come, he probably would give us a better explanation of why this is the way to do it. But one thing you could do is, so this is a C++ file, and we're including the C file. And that's doing some weird things because it kind of imports it twice or something, once as a C++ and once as a C file. So one thing you can do is change this C file to a C++ file, which we normally didn't do because SoundPipe was written in C. We don't want to change it. And then it'll give us just one error, which is that this is an incompatible type. So the way you would fix that is you would call this a custom oscillator. Instead of being a void pointer, you explicitly say, and that's because C++ is more restrictive, that really wants to know exactly what type it is. It's not going to allow the void star. So this should work. It's not going to sound any different because this is just using a but so it's working, and we fixed it by changing the C file to C++ file and made the void star this. Now that's not the normal way we do it in AudioKit, because normally we don't change C files that work cross-platforms to C++ files that are more restrictive to a certain platform. So change that back to a C file. And the other way to fix this is to say if C++ is defined, do this external C stuff, and we'll put our C declarations inside here. And that will also compile, I hope. Yeah. So that's a bug that we recently had, and that's the way to get around it. But now we can go inside here and change things about our oscillator. Now, usually DSP code is pretty intractable, and you don't want to mess around with it without knowing what you're doing, because things get loud or bad really quickly. But I wonder what we could do here that would be not too terrible. So as we compute, we might, let's just make the frequency be double what it is from the other one, so we can hear a difference. So this should be a faster and higher pitch beeping. And sure enough, it is. I love watching the Matt stuff like kind of catch up with the beeping. It's kind of a nice mesmerizing effect.
Yeah, Matt, this stuff's awesome.
Yeah,
it's sometimes hard to work on because you just play with it for a while and just lose time.
Totally.
Glad you guys like it.
Visualization is one of the greatest parts of like audio programming, because you're constantly listening to stuff, and just to see your results in a different way, it's just so rewarding. So yeah, thanks for creating that. So yeah, so now we have our own custom C level thing. It doesn't have to be SoundPipe. It can be any C inside here, but I just use something that we had available to us. And now we can do whatever we want inside here. And that's the deep dive into AudioKit's DSP. Any questions?
That was very cool. Yeah, those are really cool use cases, I think, for any kind of synthesizer that wants to use AudioKit. Yeah.
Yeah, and also for people who like they do a proof of concept in AudioKit and they string together nodes and things like that, and their app is a hit or is using too much energy or something, and they say, okay, maybe we write a test, and then we bring the actual calculations and things down into the into the C level, so they're faster, but we still have we have still gone to market fast because AudioKit made it easy, and it's kind of a bridging the gap. And that was, for a long time, that was a goal of AudioKit, to allow people to get started quickly, but then not prevent them from going deep. And I think we're getting closer to that actually as time goes on. And some people, there's a risk that you get good at it, and then you're like, oh, screw those people who are beginners. We know how it works. But I'm still forefront of my mind to try to keep the slope down to DSP like a reasonable level.
Yeah, I think this video will be really great for that. I personally am pretty intimidated by each level that it goes down to this point. And so I've never touched anything near actually creating the oscillator down here, but I really want to make it so that we have oscillators that can be like dynamically, their wavetables can be dynamically changed. And I'm thinking that as I go back through this video, I might see how to make that change for us, because that would be really cool. Like we have morphable oscillator, but it only has 4 tables, whereas we could just have one that has any number of wavetables that you can morph through.
Yeah, I mean, we just
Matt,
created one that has 2. So you could
Mhm.
create one that has like a lot. That would be one option. But yeah, if it was changeable, I don't know. That can get hard, right? Because then you're like, how do you allocate the memory appropriately? But certainly for like specific cases.
I'm looking at the same problem, Matt. So I want to do what we just did tonight and take, for example, the morphing oscillator, make it have more than 4 wavetables, add a new method that wasn't there, where we clobber the wavetables from wherever we want, Swift or whatever, for the next, and so just have an infinite, have any kind of set of wavetables that you can morph through and be able to clobber those after the oscillator's been defined. No need to destroy it or recreate it. Just clobber the wavetables, from anywhere. So tonight's tutorial is very valuable for me because I'm trying to do something similar. So I'd probably start with the morphing oscillator, and again, like make an n number of wavetables and be able to clobber the wavetables outside, like add a new method to clobber wavetables. Even while it's running. Doesn't matter if it's zippers, right? Like wavetable oscillators aren't band limited, right? Like they're just crazy. So yeah, so should probably compare notes. His little left turn, like a tangent, but Matt, your tools for tapping into a node and showing FFT and stuff is so cool. One thing to think about is if we're going to work down, if you have use cases or projects where you're going to write your own custom DSP, you might be computing a lot of different things down at this level. Like for example, here we have the tremolo, and we also have the oscillator itself. How could we visualize both of those two things? They're being computed at the DSP level. They're not at the node level. Well, what is a way for the DSP to communicate up a level to be visualized, where you can visualize all kinds of things, like all the LFOs themselves, components that go into the sound, like tremolo times the oscillator. It'd be really cool to see if what you've already built at the node level could also somehow be plumbed at a custom like DSP level, that could be really cool. I don't even know how to do that. I'm just talking out of my butt, but your visualization tools are so cool. And I'm working at this level here at the custom DSP level, and I want to use your tools, and I don't know how. So that's sort of why I'm bringing it up.
Yeah, actually, that reminds me of one thing here. So if we look at there's one thing I didn't cover that I just want to at least mention. Where do I want to start this? Not there. If I open up the flat frequency response reverse Swift. So what I showed you so far was how you can create parameters and connect parameters down low into the DSP, right? But sometimes you need to set, like have functions that set. So if you look elsewhere in AudioKit, like in the flat frequency reverb, here's a custom function that is actually calling a C level function. So this is a Swift wrapper around a C function. And this would be how you do that. Maybe I'll think about like making an addendum to this tutorial because I haven't thought about the best way to present it. But you basically, where you register parameter, you can also register these, C functions and get it so that you can call them from Swift. You send down a DSP reference and then whatever values you need to change. And so that type of thing is how you can also get, you can talk down into the C from the Swift layer. How to talk up to the Swift layer from C, like what Marcus was saying. That's a little more tricky, but I think if you look at something like like one of our analysis tools, let's see if we've got this here. Like our pitch tap. How is that getting the data back? So this is calling different AK functions like this. The pitch tracker is actually sending a bunch of different kinds of functions down in here, like say analyze and get results. So this is getting the current amplitude and frequency out of the C layer and bringing it up to Swift, not within a parameter, but within a function. So if I search for where this is used, so the pitch tap is doing this on every time it handles the tap, and it constantly getting the frequency and amplitude. So that's another way you can call into the C that I didn't exactly cover, but at least I mentioned it here. So if someone's watching to this point, they can get this. The next place to look for this type of stuff would also be the sequencer. So the sequencer has some interesting ways of calling down into the C as well. And like I said, I don't know if I'm quite ready to just talk about how that's done, but something I can sort of present for next time or some other time. And see if there's an obvious thing I can show though. Because I know that there was some talk of some use of like a circular buffer to get data back up to this level. I need to look at that and come back to you guys with a little more information on that though.
Yeah, yeah, these are like really advanced use cases. An AudioKit covers everything from like very simple out of the box use cases all the way down to the DSP. So I'm certainly interested in these. So if other folks are, it might be cool to do another one like that.
Yeah.
I haven't been leveraging functions down at DSP level, but I think just communicating. I feel like we have a really good path from UI to DSP, right? I feel like we have a lot of examples. Like all of your office hours kind of cover that.
Yeah.
It would be cool to think about the other way around, like from the DSP. Like I updated the oscillator. I computed a whole buffer full of audio samples. I computed a bunch of
Right.
low-level stuff like LFOs, manipulated them. How do I visualize what's going on in the DSP up at the UI layer? It'd be cool to think about that a little bit
Right.
too.
Well,
Again, those are super advanced use cases.
yeah. Taylor re-architected the sequencer, and he uses I think this is mostly his work. This TP circular buffer with an event queue. Now that's something where this C-level stuff is actually doing things up higher up, and so we might look into that, and that might be a good future office hours on how to use TP circular buffer to get information out of the DSP and into somewhere where other parts of your application can access it.
Yeah, that would be really helpful because I've noticed that the FTT tap comes in at a particular rate, and I'm curious if there's not some way to manipulate that, or if that's actually something to do with like the frame length versus the sample rate limiting that. But
Yeah, well, all the tap stuff is based on the AV Audio Engine taps, and it is pretty fast and pretty reliable. For a long time there, I wasn't able to get it to be faster than like 10 times a second, which is ridiculously slow. But then I added like one line of code to it that, and I think I even wrote coming in the Git comment, like you need this line for it to go fast. And once I added that, it will obey your buffer length. So if you have a short buffer length, it'll be faster. Now I'm like, we had our own tap functionality in AudioKit and actually removed it once we realized that AV Audio Engine's tap, it actually works pretty well. So I don't know, we'll get much better than what they give us there, but you can try.
Yeah, I've just got an interesting problem with, oh, sorry, go ahead. I've been talking all night.
No, it's all good. It's all good. Finish your thought.
Well, with the tap for FTT, I've been trying to make that spectrum view, and depending on your buffer size, you get less frequency content back in your bins. So I want more bins in my lower end, but I can't actually get them because turning up the buffer means it's gonna go so slow. Like I've already gotten it to the point where it is like teetering on being too slow for what I'm trying to do.
See,
and get that low frequency content.
Yeah.
So
that's the conundrum of the FFT. You know,
I just wonder how anyone else does it. You know, like I wonder how you're able to get the low frequency content. Do you maybe like band limit the low end somehow or something?
Maybe there's all kinds of hacks you could do. Like you could run multiple FFTs. Like do the one with a lot of bins for low frequency and only display that at the low. Let's say you ran it 4 times. One with a wide window for the bass, one with a second medium for treble. There could be all kinds of hacks. You could run multiple ones and only show the bins for the frequencies that make sense for that. We could we can dream up all kinds of hacks. I wanted to just touch on in Synth 1, we used audio engine, like is Mike Tyson stuff. It's a circular buffer that Ari talks about, where at the DSP level, we can lock free, push stuff into a circular buffer. For example, arrays of floats or arrays of integers or arrays of any kind of struct. And then those will get pushed into a circular buffer. And you can do that in the DSP thread without taking a lock. You can just push stuff, push. And then outside of the render thread, the buffer will be flushed at any interval you want. You could sync it with a UI interval, which is what Synth 1 does. And so that's how Synth One sort of communicated, for example, the sequencer's notes. Like I'm playing this note right now. I'm you know, blah blah blah. Like, and we didn't really exploit it. We didn't go crazy in Synth One because we were trying to make sure it worked on older devices, right? We're trying to support a lot of old OSs and weak devices. So we only limited our usage of it. The other thing it was useful for was all of the logic of the sequencer was at the DSP level. So at the UI level, a person could hold down, you know, a chord and have the sequencer on. And at the DSP level, it would say, okay, they're holding down these notes. I'm going to compute the sequencer at this moment in time. This one note is playing, but he's holding down these notes. And so it would send back up to the UI level. These are the notes that are being held down. These are the notes that are actually playing right this second. And notes that had long releases would stay visible for a really long time. So that was our way of communicating from the DSP level back up to the UI to show, you know, mostly what notes are being played on the keyboard, and then you know, the actual step of the sequencer. But I want to in new projects, I want to take that way further. Like I would love a whole bunch of the metal windows that you have for everything. I'd like to actually see, what does my LFO look like? You know, you know, we're doing, you know, I want to make really complicated LFOs where, you know, I actually need to really see what the DSP computed. I can't at the Swift layer tell you what you're going to see. So I would like 10, 20 metal windows of what's happening at the DSP layer. I don't know if that circular buffer is the right way to do that, and I don't know how other synth, you know, designers and implementers actually do that. You know, like how many synths do you see where you see everything? There's a window for everything, right? You know, so somehow focusing on getting stuff back from the DSP that was computed in real time back to the UI. I would love to spend more time with anyone who's interested in that. Try and come up with cool ways to do that. Make that a part of AudioKit.
Yeah, it'd be great. I love it when things that are really needed in the real world make its way back to AudioKit. I think that's some of the best features, rather than like just what we think somebody might want, but something we actually need. I think that's quite powerful and quite it feels right, you know.
Yeah, it'd be cool if there was some sort of idea of a node. Right now, node is at the Swift layer. But if there was some way when you're making your own custom DSP that you could designate something as a node, that you were able to visualize that the UI layer. It doesn't have to be done that way, but you know what I mean? Like you want to be able to say, I want to visualize this thing right here. It's property, it's whatever, you know. That'd be cool. This is great,
Right.
though. This is good stuff, Ari.
Thanks, guys, for showing up, and I'm going to upload this so other people can take advantage of it soon. Cool.
Sounds good.
See you guys online.
All right. Bye.
All right. Bye, everyone. Thanks, Ari.
Thanks.
Thank you.